Section 17.6 has to do with the solubility product, which is really just a special equilibrium constant. Now, if you recall back to 1210, you had a list of solubility rules. Some ionic compounds will dissolve readily in water and others will not. The reality is most of those insoluble compounds actually do dissolve. They just dissolve a teeny tiny bit. And so we could call these sparingly soluble salts. And there's a big difference between mostly insoluble and all insoluble. So these are mostly insoluble. They do dissolve a little bit. And what that means is that we could write the reaction for the solvation of an insoluble compound like chlorides, bromides, and iodides are mostly soluble with the exception of lead, silver, and mercury. So here we have lead iodide listed as insoluble on our solubility rules. But I can write an equilibrium reaction. So Pb2 plus aqueous plus 2I minus aqueous. And this is just an equilibrium which lies heavily in favor of the reactants. That means that its K value, the K for this reaction, is going to be much, much less than 1. In the case of lead iodide, it's 9.8 times 10 to the negative 9th. And so we'll call this K value, we'll call it the solubility product. The reason we call it a solubility product is because looking at this equation, we recognize that the only reactant we have is a solid. That shouldn't show up in the equilibrium expression. So we have Pb2 plus concentration times the I minus concentration. And in this case, because of that 2, we're going to have to be squaring the concentration of iodide ion. Now, KSP will sort of determine the equilibrium position, but it's not equivalent to the molar solubility. And molar solubility is in many ways a more convenient number to work with. So the molar solubility is defined as the moles of PbI2 that dissolve over in 1 liter of water. Okay, so how many moles of PbI2 are going to dissolve in every 1 liter of water? This has units of moles per liter, and so it's going to be a molar value. And so the KSP, especially when you've got squares and things, it's not actually as intuitive as you might think. But the molar solubility makes a lot of sense. If I can dissolve 1/4 of a mole in 1 liter of water, I can quickly calculate what the mass of that will be, and I can get my concentrations and things. So what would be nice is if we could go from the KSP to the molar solubility. And vice versa. Well, in order to figure out concentrations based on an equilibrium expression, we need to make an ice table. Okay, so really the I2 doesn't matter. We really only have 2 things here, the Pb2 plus and the 2I minus, and they're going to start with nothing, and here we're going to get plus x, and here we're going to get plus 2x. And so the equilibrium values are x and 2x. Now let's go ahead and plug those back into the equilibrium expression. So we have x times 2x squared, and we can simplify that to be 4x cubed. And so we need to be really careful to make sure that the 2 shows up in both places. This 2 is going to cause the change to be 2x instead of 1x. And then that 2x has to be squared. And so it's no mistake that we have the 2 in both of those places. And that 2 gets squared along with the x. That's why we end up with 4x cubed. Anyway, I'll erase this ice table now. It was pretty simple. And we can solve for this now. X is going to equal the cubed root. And on your calculator, most of you will have a cube root button. But you could also, I'll kind of write an alternative form of this. It's going to be the cube root of 9.8 times 10 to the negative 9th divided by 4. And if you don't know where your cube root button is, this is the same as 9.8 times 10 to the negative 9th over 4 raised to the power of 1/3. So if you can't find your cube root button, go ahead and use the 1/3, and we'll actually see examples where we need even higher roots. And so this is a good reliable way to take higher roots. Square root would be 1/2, cube root is 1/3, etc. And anyway, what does this give us for x? X in this case is going to be 1.35 times 10 to the negative 3rd, and that was the number of moles that would dissolve of the lead iodide in 1 liter of water. So that is the molar solubility. X represents the molar solubility. So for lead iodide in 1 liter of water, I can expect about a millimole of the compound to dissolve. All right, we could use this same sort of equation in reverse if we were given the molar solubility, and we could solve for the KSP, right? So let's take this molar solubility, 1.35 times 10 to the negative 3rd, and I know that is supposed to equal the cube root of the KSP over 4. Right, we can just kind of do this in reverse. And to be honest, it might be better to go back even further. The KSP is going to equal 4 times the cube of the molar solubility. 4 times 1.35 times 10 to the negative 3rd cubed. And actually, I didn't run this number. It's possible we'll get a little bit of a discrepancy due to rounding errors. But let's just run the number just for fun. So we're going to take 4 times 1.35 e negative 3 cubed. And that double asterisk is just how I cube things. I get 9.84 times 10 to the negative 9th, round that to 2 sig figs, and it is actually perfectly consistent. Now, we can take the molar solubility for more complex salts. So let's just look at a different example. So let's do strontium phosphate, SR3, PO4 2. That's strontium 2 phosphate. So that is a solid, and that will be in equilibrium with 3 SR2 plus aqueous plus 2 PO4 3 minus aqueous. Well, we can go ahead and do an ice table. This will be the last ice table we do because they all follow a simple pattern. Let's do the full ice table. and we don't actually care about the solid, right? So we'll start with 0 and 0. Now what will the change be? Plus 3x plus 2x. And so we have 3x is the concentration of strontium 2 plus, 2x is the concentration of phosphate. And in the end, we get the KSP then is equal to 3x cubed times 2x squared. We can simplify this a little bit. We'll cube the 3, that's 27x cubed. And we'll square the 2, that's 4x squared. And let's see, what's that going to be? 108x to the 5th. And so in the end, the KSP is equal to 108x to the 5th. X is the molar solubility. And this is one ice table where we don't have to make any simplifications. We don't have to use quadratic formula. We don't need to be assuming that x is small. X to the 5th would mess things up royally if we had like other powers of x. But with just the x to the 5th, we can solve this. So the first thing that we do need to do is figure out what is the value of that KSP. Sorry, one moment. I'm getting the slideshow ready. Okay, so here we've got table 17.2, and it gives you lots of KSP values. And one thing that I want to point out about this is that they range hugely. You've got some like barium nitrate here, about halfway down that first column. That's 10 to the negative 3rd. That's a decently large solubility. You'll find that a fair amount of your barium nitrate is going to dissolve in solution. Well, you also have things that are like calcium phosphate, 10 to the negative 33, or if we go to the next page, actually, there are some incredibly tiny numbers. Tin sulfide, 1 times 10 to the negative 70th. And what we see here is that we have just 1 sig fig. In fact, it's almost like just half a sig fig. They don't even know what digit it should be. It's just on the order of magnitude of 10 to the negative 70th. And so tin sulfide is going to dissolve to a remarkably tiny degree. And we'll actually investigate tin sulfide in particular in our quiz, in what is one of my favorite problems of the whole year. But you have some salts that are extremely sparingly soluble, this mercury 2 sulfide as well. And the way that we measure these solubility products is really remarkable in and of itself. How do you figure out this solubility product experimentally? Well, they're almost always done through electrochemical probes that are very sensitive to the presence of even tiny amounts of these metal cations. And so, whoever figured out this solubility product for tin sulfide deserves a party over at the National Institutes of Standards and Technology, because I'm sure that was an incredibly difficult measurement to make. All right, I got distracted though. What are we looking for? Strontium phosphate. It's right here, about 2/3 down the right-hand column. And this is one of those that we don't have a great measurement for, but we know that the KSP is about 1 times 10 to the negative 31st. So 1 times 10 to the negative 31st. Sorry, you can't see that. Let me get this out of the way. Okay, so we can say that 1 times 10 to the negative 31st, the KSP on this side, all the way over here is equal to 108 times x to the 5th. So x is going to equal that KSP, 1 times 10 to the negative 31st, divided by 108. Then we're going to have to take the 5th root, which if you have like a TI graphing calculator, there is an nth root button. But anyway, you may find it easier to just do this raised to the exponent of 1/5. Let's figure out what the molar solubility is. I'm going to take 1e negative 31 divided by 108, and I'm going to raise it to the power of 1/5. And I get 2.5. We really only get one sig fig here, so that I suppose it's going to be 2.2, just plain 2. 2 times 10 to the negative 7th. Moles per liter. Okay, so a very tiny amount of our strontium phosphate dissolving in 1 liter of water. Okay, so let's do one more practice problem. I hope you are starting to see how to get these equilibrium expressions in terms of X or molar solubility without doing a whole ice table. So for this next practice problem, we'll set up this relationship without the ice table. Okay, so here's the question. AgI has molar solubility of 9.0 times 10 to the negative 9th molar. Can we find the solubility product? Well, in this case, KSP is going to equal X times X or X squared. Okay, this one was simple because we have a 1 and a 1 for our cation and anion. And so they're each multiplied by 1, and they're each raised only to the first power. This gives us KSP equals X squared. And so it's really just a matter of putting our molar solubility in and squaring it. So we'll say 9.0 times 10 to the negative 9th squared. Let's find that KSP. 9e negative 9 squared. And that's 8.1 times 10 to the negative 17th. Let's see, yeah, we do get 2 sig figs there. So that is the solubility product for silver iodide.